Hello everybody, today we're going to be solving some calculus questions, specifically on concavity and inflection points and some other related concepts. Yeah, let's just dive straight into it. So here we have a question from Khan Academy, a lot of credit to that platform for such good questions. So g of x is that polynomial, let me just quickly pick another color. We have a polynomial on which interval is the graph of g concave down. So let's first understand what do they mean by concave down here. Let me quickly build an xy plane so that you can visualize all that stuff. X-axis, y-axis. Let's just say we have a random graph looking somewhat like that. So what can we say about this graph? Well, we can say that it has a couple of concaves, meaning these turns. This is one concave, this is another, this is yet another, and the fourth, which means that these concaves are gonna have some special features with which I will try to explain to you through this video. So this is a concave down, this is a concave up, and similarly this is concave down and this one is up. Well, why am I even telling you all of this? Well, because we can use all these concepts to then understand what are the inflection points, and there are a couple of other conclusions that we might come to. Well, first, let's just try to understand how the first derivative and second derivative of this random function that we chose are going to look like. So g prime of x, and here we're going to have a second derivative of the same function. Well, here in the negative plane, it is increasing until this point, right over here. And then it starts decreasing, and then derivative is 0 right over here. Then it starts increasing again. Then we have again derivative that's equal to 0, then so on and so forth. So first our function is for sure increasing until it hits derivative 0, and then it starts decreasing, meaning that it's gonna look approximately like this, and then it is still decreasing until it hits the 0 right over there. So it's gonna look like that, and then it's increasing until it hits 0 over there. Then it decreases and again increases. That's how the first derivative is gonna look like. It's just an approximation. I'm really sorry for my awesome drawing skills. I unfortunately did not really attend any art classes. Anyway, back to maths. Well, this is our first derivative, and what's the second derivative? Well, here you see the first derivative is negative. The first derivative is negative along this interval, and then it turns into positive. Well, actually, this function is a little too complicated to even care about the second derivative. Let's just specify what I mean here by inflation points. Inflation points are those points where we are just changing our signs. Well, here, let me pick another color. Here, we're changing our signs from negative to positive, meaning our second derivative changes sign from negative to positive. Those are our inflation points. I guess this is enough context for the problem, and now it's the time that we solve the problem itself. So I really hope that you got all this backstory, and now with prior experience and knowledge, we can easily tackle this question together. Okay, so we have this polynomial. G of x is equal to that good stuff. The first derivative is going to be equal to 4x cubed plus 12x squared minus 96x. The second derivative is going to be equal to 12x squared plus 24x minus 96. And here we have to make our second derivative equal to 0. Why, you might ask? Well, simply because we can look back at our example and we will see that the inflation points happen when the derivative of the second derivative of the function is 0. Here it's 0, and that's also another inflation point, and this is yet another inflation point. And the common pattern is that the derivative of the second derivative of the function should always be 0 if you want to find the inflation points. So we're going to make all of this equal to 0. Then we can factor out 12. This is going to be 8. Then, since 12 doesn't really play any kind of role here, let's just eliminate it. And here we can use many ways of finding the solution, but I'm just gonna use a basic discriminant, nothing too fancy. Well, it's gonna be b squared minus 4ac divided by 2a. Our a is just 1 here, so it's gonna be just 2. Here we're going to have negative 2 plus, this is negative 32. 4 minus 32 is going to be equal to 36 divided by 2. Negative 2 plus 6 divided by 2. And here we're going to have our final answer, 2. And here, negative 2, we just change the sign. It's going to be minus now. This is negative 4. So those are our two potential candidates for inflation points. Don't immediately jump into conclusion and say that these are inflation points, because they're not. These are just candidates. Some of them might fall short of meeting all the requirements that inflation points should meet in order to be themselves. So we have negative 4, we have 2. As in the previous video, we're going to indicate it through just this dash. And then let's just pick some arbitrary values that are in the neighborhoods of these two values. Well, we can have 0, we can have 3, and we can have negative 5. If we plug in 0 in here, we're going to get negative 96, meaning the derivative is decreasing. So we're going to show that. Then if we apply 3, we're going to have 12 times 9 plus 24 times 3 minus 96. This is 108. This is 72. Well, for sure, the sum of these two numbers is surely going to be greater than 96. So this is going to be positive, because the derivative is positive. That's why the function is increasing. And then when it comes to negative 5, if we try to apply it, we're going to get 12 times 25 minus 24 times 5 minus 96. Here we have 300. Here we have what is it, 120. Yeah, minus 96. Well, again, these two aren't gonna be large enough to be greater than 300. That's why we have positive here. Well, what was the question? Now, remember that this is, here we have concave down, and here we have concave up. Depending on the question, the answer is going to be either -4 or 2. The question is concave down, so the answer should be -4. Oh, they're asking for an interval. Okay. Well, it's gonna be it is going to be wait, I'm really confused. What's going on? Did our calculations go wrong somewhere? Or was it all correct, but I'm just an idiot who cannot figure out the answer for such a simple question? Well, I really did not expect that I will let you down this way. Turns out that the explanation would be a little different. Well, in our case, concave down would be an equivalent of this sign, meaning when our second derivative is negative, while concave up will mean this sign up, that is pointing upward. So our answer is going to be x is between 2 and -4, which is exactly what we see in answer choice B. So let's not make such a silly mistake again, and let's just dive straight into the second question, which is going to be a little more complicated, but that's the whole reason why we're all here, isn't it? So f of x is equal to that good thing, on which interval, I guess, is the graph of f of x concave up. Well, now we're looking for some inflation candidates which have a sign that is upward, not downward, which was the case in the previous example. Let's don't confuse those two with each other. Well, again, we have to find the second derivative, for which we would need the first derivative. Let's figure it out. Here we will use the quotient rule, and I guess a little bit of a chain rule in the process. Well, the derivative of the first function, which is the function is constant, so it should be 0. Well, we're not going to care about this part. It's going to be 0 minus just the first function times the derivative of the second function. And here we have just the second function squared. Let's just try to simplify it. It's going to be just 81 times, well, here we have to use the power rule. We get our exponent to the front. Let me just create a clear borderline. This part is going to stay the same. Denominator stays the same because we don't really need to simplify this. Back to our numerator, we got our exponent to the front, and then we have to decrement it by 1, which is going to get us x plus 5 to the negative 2/3. Here it's going to be equal to 27 over that thing, and all of it divided by this stuff. Well, here we again can simplify this. It's going to be 27 over cube root of x plus 5 to the 4th power. And now we have to find the second derivative. Again, we are going to skip this part because the derivative of the constant is always 0. Then it's going to be minus just the first function times the bottom function, the derivative of the bottom function, times the derivative d over dx of this function. I really need to draw my 3 more clearly. Then we have on the bottom this function, again squared, which is going to get us an 8 out here. Then again we have to simplify all of this because it looks really messy right now. Here we're going to have 4/3 times x plus 5 to the 1/3 power. Well, the reason why there is no continuation to the chain rule is because the second half would be the derivative of the inside function, which is going to be just equal to 0. That's why I'm not really writing it down, because either writing times 1 or not writing it is not going to make any difference. All of it divided by this thing. I'm not going to try to rewrite it. Then we have here we have some opportunity and room to simplify. We have negative 36 times, well, let's just make it look a bit better. We have this function, all of it over yet another expression. Here we're going to have negative 36 divided by cube root of x plus 5 to the 9th power. Well, these two get simplified. We get negative 36 x plus 5 cubed. And now, what are some x values when our second derivative is going to be equal to 0? Well, we only have x equals negative 5. So let's just quickly draw the number line, and we're gonna utilize all this problem solving stage of our problem. We have negative 5. Let's just pick some values around negative 5. It's going to be 0 and negative 10, for instance. And then our second derivative is going to look somewhat like this in its most simple form. So now we just have to plug and play. Again, I'm going to showcase that this is the candidate for inflation points. If we plug in 0, we're going to get negative derivative, so it's concave down. Let me write it down. Concave down. If we plug in negative 10, we're gonna get concave up. Concave up. This stands for concave up, of course. And now let's look at the problem. What does it ask? Concave up. So the answer should be negative 10. Well, they're asking for the interval. The interval is going to be x is between negative infinity and negative 10. This is where it is concave up. And let's move on to the last problem for today. Let h of x be that function, for what values of x does the graph of h have a point of inflection? Okay, they are now asking for the point of inflection, not for the interval when the function is concave up or down. So I guess this problem is going to be a little easier, but it definitely has a different way of testing our knowledge of concavity in calculus. Again, the same steps. First we have to find the first derivative, then the second derivative. Quite simple. Here we're going to have, for the first derivative, we're going to have negative 3 seconds times 4 times x third plus 18x squared plus 144x. If we simplify it, we're going to get negative 6x cubed plus 18x squared plus 144x. Then h prime prime of x is going to be equal to negative 18 times x squared plus 36x plus 144. And we have to make our second derivative equal to 0 if you want to find the inflection points. I'm really sorry. Why am I confusing this? The inflation is a concept from economics, whatever. Well, we can factor out 18. Here we're gonna have negative 2x, negative 8, yep, is equal to 0. Again, we can use the discriminant. 2 plus 4 minus, well, it's going to be just 32 divided by 2. We have 2 plus 6 divided by 2, which is equal to 4. And x2 is equal to negative 4 divided by 2, which is negative 4, I'm sorry. Well, we can just check it by plugging it in, but that's going to be too long. I really do trust my own arithmetics. Let's just move on to next stage. The number line, as always, is going to be very helpful. We have -2, we have 4. In between, let's just pick 0. From that side, we're going to pick 5, and from the left side, we're going to pick a negative 4, for example. Here we have the simplest form of our second derivative. We're going to use this one to plug and play again. If we plug in 0, we're going to get 144, which is of course concave up. If we plug in 5, we're going to get negative 18 times 25 plus 16 times 5 plus 144. What is it equal to? Let me quickly use decimals for this. Negative 18 times 25 plus 36 times 5 plus 144. It's equal to negative 126. Well, this is definitely concave down. And then we have negative 4, negative 18. Let me just try to separate this part from the rest. Times 16 minus 36 times 4 plus 144. Well, this one is definitely going to be concave down because these two numbers are definitely gonna supersede anything that this one can propose. So this is concave down. And now we have to find the inflation points, which are gonna be -2 and 4. Because remember that inflection points, I'm sorry, why do I keep saying inflation points? Inflection points are those where the second derivative is changing its signs. And in this specific case, in both scenarios, meaning when x equals -2 and when x equals 4, the signs are changed. Because when it comes to -2, it changes from negative to positive. And when it comes to 4, it changes from positive to negative. That's why our answer would be x is equal to -2 and 4. Well, it turns out that both of our inflection points candidates turned out to be the real points. And now let's just quickly pick the answer. It's gonna be C and B. That is all that I wanted to talk about today. I really hope that you found this content useful. If there is anything else that you would love me to explain, please leave it in the comments below, and make sure to subscribe and leave some positive messages in the comments to support me and to also motivate me to keep doing all this stuff. Thank you for everything, and I see you next time.